Hello, this is video for the Quartz steps. First, open the Quartz. This version is 18.1. Quartz is opening now. Then first, File, New Project Wizard. Then Next. Here we will choose the working directory, the name of the project, and the top level design entity, and all of them should be the same name. So here we will go to this folder and create a new folder here. We will make the code of counter, so we should write counter underscore 1. Then we will choose it, select folder, and here also we will write the same name of the working directory. Then next. Here in this tab, you should choose whether you will make an empty project from scratch or you will use one of the projects on the templates. Here we will create our project from scratch, so we will choose empty project. Then next. This window, if we have files, .v files, if we will work Verilog from other projects and we want to add it into our project. In our case, we don't have any files that we want to add it, so we will press next. Here, we will choose the family, the device, and the board settings. So here I will choose Max10, and I will choose this device, and then next. Here, if you want to use a special simulation tools, design tools, but here we will use the default tools on Quartz. Next. Here's the summary for all what we have chosen. Then we will click finish and the project will be created. In this project, we will use the Verilog as the HDL language, the hardware descriptive language we will use. So here we want to create the .v file that we will write our code on. So we will click here on this white paper, and then there is many choices that we have here. So we will begin with the design files. The language that we will use is the Verilog, so we will choose Verilog HDL file and then click OK. Here's the .v file that we will write our code. Then here's our code. We can go quickly for all over the code. This is a code of a counter. So for the counter to works, we will have 3 inputs: the clock, which is the clock that we will make the synchronization for the counter, and reset, enable, and the output, which is counter out, will be the output of the counter. Here in our code, it's a 4-bit vector output of the counter, which is a 4-bit counter. So it will, all the numbers will be represented by 4 bits. Here's the definition for our inputs: the clock, reset, and enable, and the output, which have the counting, and its size 4 bits, so the range will be from 3 to 0. For the inputs, we will define them as a wire, so wire clock, wire reset, wire enable, and then the output, it will be defined as a register, so that every count that produced from the counter, it will be saved on the register. And logically the range will be the same size of the counter out, which is 3 to 0. Then we will begin our functionality. So here the counter will work by some conditions. The first condition, that the clock will be equal 1, which is the start of the positive age. So here we will write here on the always add condition positive age clock. So once the positive age starts on the clock, input, so the counter begins count. Also, there is another condition that if the reset equals 1, so the counter out will be zeros. But if the reset equals 0, the counter can begins counting. Also, in the same time, there is another condition. So we use here else if, that the enable should be equal 1. So if the enable equal 1, so the counter output will be increased by 1, and the output will be put on the counter out. Here the #1, it's a delay of 1 unit, and the unit will be defined on the simulation. Then end, and this is the end of the f, and else f, and this is the end of the else f, the begin of the else f, and this end, it's the end of the begin here, and in module to end the modules. Now we want to check the code, so we will press here the play button to make the compilation for the code. So we will press here like this. Yes, as you see here, the name of the file, change it to counter_1. Let me here cancel. I want to make sure that the name of the top module the same. So this is not the same name, so I have to change it. This name, I have to change it to be the same name here of the working directory, the project, and so on. So here I will write the same name, counter_1, and then press save. So it will be saved by this name, counter_1, and here the top level entity, the same name, which is the module, and the file will be .v, which is the extension for the Verilog file. Then save, and then I will press the play button here, which is the compiling. We are waiting for the compiling to be ended. Okay, now our code is 100% correct, and we can simulate the code to make sure that the code is functionally working. So here we will choose this white paper another time, but for this we will go for the verification debugging files section, and we will choose the final one, which is the university program VWF. And then OK. So this window is opened. We should insert here the inputs and outputs of our code. So we will go here and then right click, and then choose insert node or bus. And then we will choose node finder, then list. So as you see here, this is the list of the inputs and outputs. So we will send it here, then okay, and okay. So here, this is the inputs and outputs. We have here the clock enable and reset, and the counter out, which is the output of the counter. In the beginning, I want to change the value of the counter out from this x's, which is x means unknown, because this is the first time that the code will be working. So I will leave here the enable 0 and reset equal 0. And here I want to input the clock, so I will choose here the clock and go here for the tab of the clock, which called override clock. Here the period of the clock is 10 and the offset 0 and the duty cycle is 50. So it will be 5 nanosecond equal 1 and the other equal 0. So this is the clock we can make here, zoom. So we will, the clock be more obvious here. 5 nanosecond 0 and 5 nanosecond 1. And then I will simulate it, so the counter out will be changed to be zeros. Before that, to change the counter out to be zeros, the reset will have to be changed also to be 1, as we write here in the code that if reset equals 1, so the counter out will be 4 zeros. So here we should change the reset to be equal 1. So here's 1, and then we will click run functional simulation. Yes, and yes, here. So here, as you see on the simulation, I will zoom in here. To be obvious, I have to make zoom out. So here, when the reset, it will be 0, so the counter out value changes from the 4 x's to 0 x's, so to a value of the zeros, which means that this is the first condition on the code, that when the reset equal 1, the counter out is the values of the counter out will be 4 zeros. Then here we want to begin to count. So I will change the value of the reset to be equal 0. This is the simulation file, so we will not change here. We will change here. So here the reset, we will change it to be equal 0, and the enable will be equal 1. Then we will press run functional simulation, so we can modify the inputs. Yes. So here, okay. Here's the inputs, and we want to make zoom in so we can see the numbers. Okay, so here the counter begins to count. So it's 4 zeros, then 0, then 1, 2, 3, 4, 5, and so on until it goes to the last number, which is 4 ones, which is 15, and the counter will begin to starts from 0 again, 1, 2, and so on. Okay. So here we wrote the code of the counter by Verilog in the Quartz, and we simulated the functionality. And we make sure that it's working successfully. Okay, thank you.